Hello and welcome to our second week's lesson. This week I'm going to cover 4 chapters: intervals, Cartesian coordinates, functions and sigma notation. Again, hopefully the material in this week's lesson will be familiar to you, so hopefully this should be a revision lesson for you from high school maths. We start with an interval. What is an interval? An interval is just a subset of the real numbers which satisfies 2 rules. Rule number 1 is the subset must contain at least 2 numbers, and rule number 2, the subset cannot have any holes in it. So, for example, the set of all real numbers x, which are strictly bigger than 6, is an interval. We can draw a picture of this subset. This blue line is my picture of this interval. Starts at 6 and goes all of the way to infinity. There are no holes between 6 and infinity. So this is an interval. Because the number 6 is actually not in this set, because we're using the notation strictly greater than 6, we use this open circle at 6. Another example would be the set of all real numbers x such that x is between -2 and 5. And again, we can draw a picture of this set. It's the line joining -2 to 5. For this set, the endpoints are in the set. -2 is in the set and 5 is in the set. To show this in the picture, we draw a filled-in circle at -2 and at 5. This is another set, the set of all real numbers x, such that x is not equal to 0. We can draw a picture of the set. It's all of the real numbers between -infinity and infinity, except 0. We have a hole at 0. Because there's a hole in the middle, this is not an interval. We can classify a finite interval in 3 ways. It can be closed, half open, or open. If the interval contains both its endpoints, then the interval is called closed. If it contains one of its endpoints but not the other one, then it's called half open. If it doesn't contain either of its endpoints, then it's called open. Let's look at some examples. For example, the set of all numbers x, the set of all real numbers x, such that x is strictly between a and b. I can draw a picture of this. This is the line joining a to b, but because a and b are not in the set, we draw an open circle at a and an open circle at b. Because the endpoints are not in the set, this set is called an open interval. We want a short way to write this, a nice short notation. We use the notation rounded bracket a comma b rounded bracket. Then the second example in this table. The set of all real numbers x such that x is between a and b. This set contains its endpoints a and b. So filled-in circle at A, filled-in circle at B in the picture. Because both endpoints are included, this interval is called closed. We show that the interval is closed using square brackets. We can use the notation square bracket A comma B square bracket. Or in the bottom 2 lines of this table, we have half open intervals. Each of these intervals contains one endpoint, not the other one. For example, square bracket a comma b round bracket contains the endpoint a, but does not contain the endpoint b. And round bracket a comma b square bracket is the opposite. This interval contains the endpoint B, but does not contain A. An infinite interval, that's an interval which goes to infinity or minus infinity, can be open or closed. It's closed if it contains a finite endpoint, and it's open if it's not closed. It's not possible to have a half-open infinite interval. That an infinite interval must be open or closed. There's one exception to this rule, as rules often have exceptions. The whole real line, that's every real number, is an interval which is both open and closed. Why is this? This is so that if we go to higher mathematics, the rules we use for higher mathematics work if we say that the whole real line is both open and closed. So really it's just so that more difficult maths works. First line on the table, round bracket A comma B, infinity round bracket. A set of all numbers x such that x is strictly greater than A. Here's a picture of this interval. The interval starts at A and it goes all of the way to infinity. Because A is not included in this set, this is an open interval. Second interval is closed. Square bracket A comma infinity round bracket is a closed interval because A is included in the interval. We might have round bracket minus infinity comma B round bracket, which is open, round bracket minus infinity comma B square bracket, which is closed, or round bracket minus infinity comma infinity round bracket, which is every real number, every number between minus infinity and infinity. But as I said on the previous page, we need this to be both open and closed. Sometimes we might want to combine two intervals together using the union notation. For example, we might have the closed interval from -8 to -2 and the closed interval from 2 to 8, and then we might want to combine them together to have the closed interval from -8 to -2 union the closed interval from 2 to 8. This whole set altogether is not an interval because, of course, there's a hole in the middle. 0 is in the middle, but it's not included in this set. Chapter 5 is about Cartesian coordinates. Again, I'm going to be quite quick because I'm assuming that you've studied this at school. This blue horizontal axis we call the x-axis. The vertical red axis is called the y-axis. And the point where these two axes cross is called the origin, which we're going to call O. We can describe the positions of every point in this two-dimensional plane using two numbers. For example, the point P we can describe using the coordinates 4, 3. This means we start at the origin. First we go to the right 4 units and then we go up 3 units. Or if we start at the origin and we go left 2 units, because we go left, we write -2, and then up 4, we get to the point Q, which we say has coordinates -2, 4. The set of all points in the plane is denoted by r squared. You can think of this as we have a real line from left to right, and we have another real line from bottom to top. We have two real lines, or to say this another way, we have two numbers. We have x is a real number and we have y is a real number. To say that we have a pair of real numbers, we write r squared. For example, let A 2 minus 1 and B 3 1 be points in R squared. Draw the triangle OAB. O is the origin, the point 0, 0. For A, we go 2 to the right and then down 1. Here's the point A. B is the point 3, 1. Start at the origin, go to the right 3 and then up 1 to get to this point. And then we'll have to draw the triangle with vertices at these 3 points. I've drawn it here in blue. Draw the region of points which satisfy x is between 1 and 3. We want to find all of the points x, y which satisfy this equation. X must be between 1 and 3. Y can be any number. First, I'm looking at x equal to 1. This is a vertical line. All the points where x is equal to 1 is a vertical line. I can look at x equal to 3. This is also a vertical line. If x is between 1 and 3, x must be between these two lines. So x must be this vertical strip between 1 and 3. Another example. Draw the region of points which satisfy x is between 1 and 2, y is between 1 and 3. Again, we use our same strategy. First, I look at x equal to 1. This is the vertical line x equal to 1. I can look at x equal to 2, again, a vertical line. And we do the same for y. Y equal to 1 is a horizontal line. Y equal to 3 is a horizontal line. Like this. And the question says and. It doesn't say or, it says and. We want all of the points where x is between 1 and 2 and y is between 1 and 3. So we want all of the points which are between these 4 lines. In other words, we want this rectangle, which I've drawn in blue. We can measure the distance between 2 points using Pythagoras' theorem. Let's suppose we have point P1 with coordinates x1, y1 and coordinates P2. So point P2 with coordinates x2 and y2. And let's suppose we want to measure the distance between P1 and P2, which for distance between 2 points, I'm going to write it like this. 2 vertical lines, P1, P2, 2 vertical lines. By Pythagoras, we know that if we measure the base of the triangle and the height of the triangle, the base squared plus the height squared is equal to the hypotenuse squared. So the distance between P1 and P2 must be the square root of x2 minus x1 squared plus y2 minus y1 squared. For example, we can calculate that the distance between A and B. Go through this calculation and we find that the distance between these 2 points must be 5. Chapter 6, which is a long chapter, is about functions. In this course, I'm going to be writing y is equal to f of x lot. In English, I read this as y is equal to f of x. Here f is the function, x is the independent variable. Any number that we can choose any number that we want within its domain. Y is the dependent variable. After we choose x and f, we calculate the y. So y is dependent on f and x. Formally, what is a function? A function from a set D to a set Y is a rule, and it's a rule which assigns a unique element of Y to each element of D. The set D, that's all of the possible values of x, is called the domain of f. The set Y is called the target of f. And the set of all possible values of f of x is called the range of f. We can write a function like this. If f has domain D and target y, we can write that f colon is a function which from D to y. For example, we might have a function f which maps from the real numbers to the real numbers and which has the formula f of x is equal to x squared. Or we might have a different function, f which maps from the open interval from minus infinity to infinity. Remember, this is just the same as r, but this time I'm mapping to the closed interval from 0 to infinity. And again, I'm using the same formula, f of x is equal to x squared. Because the second function has a different target, it's a different function. You might think of functions, domains, targets, and ranges like this. We have our two sets, D and Y. The function is mapping from D to Y. So we might think of a function as lots of little arrows which take a point in the domain into some point in Y. Point x, we might say, goes to this point, f of x. Some point t, an arrow means the function takes us to a point, f of t, and a point p might go to f of p. If we look at all of the possible endings of the arrows, we might not get to all of y. We might only get to some of y. The ends of the arrows is the range of f. And the range of f is a subset of the target y. Or we might think of a function like this. We might think of a function as some sort of machine. We put a number into the machine, we put x into the machine, and out comes a different number, f of x. X is a member of the set D, f of x is an element of the set Y. Let's go through some examples. First of all, I want to look at the function x squared, y is equal to x squared, where the domain is all of the real numbers, the open interval from minus infinity to infinity. And I want to calculate the range of this function. What numbers is it possible for y to be? Can we get y is equal to 0? And the answer is yes. We can get y equal to 0 by choosing x equal to 0. So y must be in this range. So y equal to 0 must be in this range. Could we get y equal to 1, say? The answer is yes. We could choose x equal to 1. Could we have y is equal to 1,000,000, say? Yes, we could choose x equal to 1,000, and then x squared is equal to 1,000,000. All of these positive numbers we could get. What about y is equal to -4, say? Is it possible to choose some number x such that y is equal to -4? And the answer is no. There are no real numbers x which make x squared equal to -4. Which numbers can we make using x squared? We can make the positive numbers, the numbers between 0 and infinity. So the range of this function, the set of all possible y, must be a closed interval between 0 and infinity. Next function. Y is equal to 1 divided by x squared, where the domain is the set of all real numbers except x equal to 0. Why except x equal to 0? Because we can't do 1 divided by 0. What numbers can we make using 1 divided by x? We can get any positive number that we want. If I wanted, say, y is equal to 1/2, that's okay. We can do that. We just choose x is equal to 2. What about if I wanted y is equal to 100? Yeah, that's okay. We just choose x is equal to 1 divided by 100. We could get any strictly positive number. We could also get any strictly negative number. If I wanted to make y is equal to -2, that's okay. Just choose x is -1/2. But we can't make 0. Is it possible to make y is equal to 0? The answer is no. We can't choose a value of x such that 1 divided by x is equal to 0. So the range must be the same as the domain. Every real number except 0. The third function, the square root of x. For domain, I have all of the non-negative numbers. That's the closed interval between 0 and infinity. Using the square root function, we can also make every number between 0 and infinity. Y equal to the square root of 4 minus x squared. This time I want to use a domain closed interval between -infinity and 4. We can't take the square root of a negative number in the real numbers, so we can't have any numbers which are bigger than 4. What is the range of this function? Again, and I'll leave this for you to think about, it must be the closed interval from 0 to infinity. Square root of 1 minus x squared. Again, we can't take the square root of a negative number in the real numbers, so the biggest possible domain that we could use is the closed interval between -1 and 1. What numbers can we make? Let's think. Let's look at x as -1, x is 0, and x is 1. If x is -1, I'm going to get 1 minus -1 squared, or 1 minus 1, or 0. Square root of 0 is 0. What if I choose x is equal to 0? I get the square root of 1 minus 0, or the square root of 1, which is 1. If I choose x is equal to 1, and again, I get the square root of 1 minus 1. The square root of 0 is 0. In fact, the range of all possible values of y is the closed interval between 0 and 1. Y is equal to x squared, but on 3 different domains. First of all, if we use the domain closed interval from 1 to 2, what possible values of x squared could we get? 1 squared is 1, 2 squared is 4. We can get every number between 1 and 4. If we have the closed interval from 2 to infinity, again, 2 squared is 4, and infinity squared is infinity. We can get every number between 4 and infinity. What about this one? Minus 2 squared is 4. Minus infinity squared is plus infinity, because minus multiplied by minus is plus. Again, y can be any number between 4 and infinity. And final two examples, y is equal to 1 plus x squared, and y is equal to 1 minus the square root of x. I'll leave this for you to think about. If you're rewatching the video, pause the video now, think about what the range should be. I'm just going to tell you that the answers. We can talk about graphs of functions. What is a graph? A graph is a set containing all of the points x, y, which satisfy the equation y is equal to x squared. And we can draw a picture of the graph of f. For example, graph the function, which is another way of saying draw the graph of the function, y is equal to 1 plus x squared over the interval, the closed interval from minus 2 to 2. In other words, x can be any number between minus 2 and 2. Draw the picture of the graph of y is equal to 1 plus x squared. The first thing to do is to make a table of xy points which satisfy the equation. We're going from minus 2 to 2, so it makes sense to do the ends. And some numbers between minus 2 and 2. I choose to use minus 1, 0, 1, and 3 over 2. For each of these, we can calculate y. For example, if x is minus 2, y is 1 plus minus 2 squared, or 5. If x is minus 1, we get y equal to 2. If x is 0, we put 0 into the equation. Y is equal to 1 plus 0 squared, or 1, and so on. We can plot these points on axes. The point x is minus 2, y is 5. The point x is minus 1, y is 2, etc. And then step 3, we can draw a smooth curve through these points. This is the graph of this function over the closed interval from minus 2 to 2. Not every curve that you can draw in R squared is the graph of a function. To decide which is the graph of a function, we can use the vertical line test. The vertical line test says that every vertical line that we can draw can intersect the graph of a function at most one point. So, for example, in the left picture, every vertical line we draw intersects this graph at most one point. In the right picture, I've drawn a circle, and you can see that some vertical lines that we draw intersect the circle at 2 points. This tells us that a circle is not the graph of a function. Briefly, I want to talk about piecewise defined functions. These are functions where we can use a different formula for the function on different parts of the domain. The function absolute value of x, we can write this way. If x is a positive number, we can write absolute value of x is equal to x. If x is a negative number, we write that the absolute value of x is equal to minus x. And the graph of this function looks like this. Another example. Let's suppose we can define a function like this. F of x is equal to minus x if x is strictly less than 0. F of x is equal to x squared if x is between 0 and 1. F of x is equal to 1 if x is strictly greater than 1. The graph looks like this. First part of the function, the green part, y is equal to minus x. Then we have y is equal to x squared on the red part. And then on the orange part, we have y is equal to 1. There are more examples in the lecture notes. We can classify some functions as increasing or decreasing functions, or neither. Let capital I be an interval and look at the function f, which maps from this interval I to the real numbers. A function is called increasing if, as we go from the left to the right, the function is always going upwards. Precisely for any two numbers that we want to choose, we say that the smaller number is called x1 and the bigger number is called x2. We must always have that the function at x1 is smaller than the function at x2. For a decreasing function, everything is the same except we swap less than to greater than, because we want the function at x1 to be bigger than the function at x2. This function is an increasing function. As we go from the left to the right, the function is always going upwards. So it's an increasing function. This function is decreasing. As we go from the left to the right, the function is always going down. This function goes up, and then it goes down, and then up, and then down, and so on. It's not always going up. It's not always going down. So it's not increasing, and it's not decreasing. Some functions are even functions. Some functions are odd functions. Let me just remind you of the numbers. The numbers 2, 4, 6, 8, 10, etc. are called even numbers. The numbers 1, 3, 5, 7, 9, etc. are called odd numbers. A function is called an even function if it satisfies this rule for all x in its domain. F of minus x is the same as f of x. A function is called an odd function if it satisfies a slightly different rule. If for every x in the domain, we have that f of minus x is equal to minus f of x. For odd and even functions, these are the two things that we're going to be looking for. Either f of minus x is always equal to f of x, or f of minus x is always equal to minus f of x. For example, the function f of x is equal to x squared. To understand this, we start with f of minus x, or minus x squared. We can simplify this to x squared, which is the same as f of x. Because we always have f of minus x is equal to f of x, we can say that this function is an even function. Even functions are functions where the left side of the graph is a mirror image of the right side of the graph. If you have a function where you could always put a mirror on the y-axis, then you have an even function. Next, I want to look at f of x is equal to x cubed. Again, to understand this, we start with f of minus x. It's minus x cubed, or minus x cubed, which is the same as minus f of x. Because we always have the f of minus x is equal to minus f of x, we have an odd function. What do the graph of odd functions look like? They look at functions where if we take the function and we rotate by 180 degrees, we have the same function. Anytime we have a function where you could take its graph and you could rotate it 180 degrees about the origin, you have an odd function. Next example. Think about x squared plus 1. Is this function even or odd or neither? To understand this, we start with f of minus x. And we go through the calculation and simplify, and we find that this is the same as f of x. So therefore, this is an even function. Second example. What about x plus 1? Is this an even function, an odd function, or neither? This time, instead of looking at every x, I'm just going to look at one number. I'm just going to look at minus 2 and 2. I can calculate g of minus 2, that's minus 1, and I can calculate that g of 2 is equal to 3. Then notice what we have. G of minus 2 is not the same as g of 2, so this function is not even, and g of minus 2 is not equal to minus g of 2. That tells us that the function is not odd. So the function is neither even nor odd. If you wanted to prove that a function is even or prove that a function is odd, we need to do it for every x. So we start with f of minus x. If you're trying to prove that a function is not even and not odd, you don't need to do it for every x. You only need to find one number where the rule doesn't work. Next, I'm going to quickly run through some types of functions. Linear functions are the functions which are straight lines, which have the formula. The function is equal to mx plus b for some numbers m and b. For example, we could have m is a half, b is 0. The function y is equal to half x is a linear function. Or the blue line, let's suppose m is minus 2 and b is equal to 1. Y is equal to minus 2x plus 1 is a linear function. These are all straight lines, hence the name linear. Power functions. F of x is equal to x to the power a. In English, we say x to the power of a. Are power functions. Here, a can be any real number. We go through very quickly. If a is 1, we have y is equal to x. If a is 2, y is equal to x squared. Y is equal to x cubed, or y is equal to x to the power 3. Y is equal to x to the power 4, and so on for positive integers. For negative numbers, let's suppose a is minus 1. We get x to the power minus 1, or to write this another way, 1 divided by x. If a is a half, say, we get x to the power of a half, which we can write as the square root of x. X to the power 1 over 3, or the cubed root of x. X to the power 3 over 2. X to the power 2 over 3, and so on. Let's suppose we combine lots of power functions together. X to the power n is a power function, x to the power n minus 1 is a power function, and so on. Let's suppose we have some constants, an minus 1, etc. and we write a function like this. This is called a polynomial. The domain of a polynomial, or by which I mean the biggest possible domain of a polynomial, is always the whole real line. If we have polynomial divided by polynomial, then we have a function called a rational function. For example, this function at the bottom, 2x cubed minus 3 divided by 7x plus 4. We have polynomial divided by polynomial. This is a rational function. A to the power of x for a real number a, which is strictly positive and not equal to 1, is called an exponential function. The inverse of an exponential function is a logarithmic function. Log base a of x. Y is equal to log base a of x if and only if x is equal to a to the power y. And again, here a is a constant. A is a real number which is strictly positive and not equal to 1. Angles. We should briefly discuss ways to measure angles. There's two ways to measure angles. We could use degrees or we could use radians. Degrees you will studied a lot at school, but later in this course we're going to need to use radians. Look at the left picture. Imagine we have a circle of radius 1. And let's suppose I'm interested in the angle between these two lines. What we can do is we can measure the distance around the outside of the circle. And this distance we call it the angle in radians. For example, in the right picture, this angle is 180 degrees, or we could say that this angle is the distance around the outside of a half of a circle, or pi radians. Pi radians is the same as 180 degrees. We could divide by pi and say that 1 radian is the same as 180 divided by pi degrees, or 1 degree is the same as pi divided by 180 radians. At the bottom there are 3 common angles. 45 degrees is the same as pi over 4. Now you will note that when we use degrees, we show this by using this small circle. When we use radians, we don't use anything. If you see an angle with no little circle, it means that we're using radians. 60 degrees is the same as pi over 3. 90 degrees is the same as pi over 2. In calculus, we have to use radians. When we get to part 4 of this course, and when we're doing calculus, every time you see an angle, it's going to be in radians. The reason is, and I'll show you this to you when we get to part 4, calculus doesn't work if we use degrees. When we do calculus, we have to use radians. The trigonometric functions. Imagine we have a circle of radius r. Let's suppose we have a ray, this green line, intersects the circle at the point xy. And let's suppose we know that the angle between the x-axis and this ray is theta, either theta degrees or theta radians. We can define the sine function and the cosine function. sine of theta is equal to the number y divided by the number r, and cos theta is the number x divided by the number r. After we have sine and cos, we can define the other four trigonometric functions. Tan means sine divided by cos. Sec is 1 divided by cos. Cosec is 1 divided by sine. And cotan is 1 divided by tan. There's two common ways to write cosec. Some people write cosec. Some people write csc. In this course, I'm going to use the first one, cosec. When you write your exams, I don't mind which one you use. Use whichever one you're more familiar with. Let me quickly note that tan and sec are only defined if cos theta is not equal to 0, because we can't do 1 divided by 0. Likewise, cosec and cotan are only defined if sine theta is not equal to 0. We can find sine 45 degrees or sine pi over 4 using this triangle. Start with a right angle triangle, base 1, height 1. By Pythagoras, the other side of the circle must be square root of 2. Then sine 45 degrees must be 1 divided by square root of 2. Cos 45 must be 1 divided by square root of 2, because cos is x divided by r. After we have these two, we can do the other four. Remember that tan is sine divided by cos, sec is 1 divided by cos, cosec is 1 divided by sine, and cotan is 1 divided by tan. We can also use a simple triangle to find sine of 60 degrees and cosine of 60 degrees. Let's suppose we start with an equilateral triangle of side 2, and let's suppose that we cut this triangle in half to get this big picture. Then we have triangle of base 1, hypotenuse 2, and using Pythagoras, the third side must have sides square root of 3. This angle must be 60 degrees or pi over 3. This angle must be 30 degrees or pi over 6. Sine is then square root of 3 divided by 2. Cos must be 1 divided by 2. And as soon as we know sine and cos, we can calculate the other four. Tan 60 degrees must be square root of 3. Sec 60 degrees must be 2. Cosec 60 degrees must be 2 divided by the square root of 3. And cotan 60 degrees, which is 1 divided by tan, must be 1 over root 3. The graphs of sine and cosine look like this. The final chapter of today's class, which is quite a short chapter, is about sigma notation, which again we will need later in the course. Let's suppose we have lots of numbers we want to add up. I suppose we have a number A1 plus a number A2 plus a number A3 plus a number A4. It can be quite a long calculation, quite a long way to write if we have A1 plus A2 plus A3 plus A4, etc. etc. We want an easier way to write a sum like this. And the way that we write it is sigma from k is equal to 1 to n of a subscript k. This symbol is Greek letter capital sigma. K equal to 1 at the bottom tells us that the sum starts at k equal to 1. In other words, it tells us that the first one in the sum is A1. The n on the top tells us that the sum finishes when k is equal to n. The end of the sum is an. For example, if I have 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared plus 7 squared plus 8 squared plus 9 squared plus 10 squared plus 11 squared, we can write this as the sum from k equal to 1 to 11 of k squared. Or if I'm doing f of 1 plus f of 2 plus f of 3 plus etc. plus f of 99 plus f of 100. Instead of writing this in this long way, we could just write the sum from k is equal to 1 to 100 of f of k. Or going the other way, the sum from k is equal to 1 to 5 of k means 1 plus 2 plus 3 plus 4 plus 5, and we can add this up and find this 15. 3 more examples. The sum from k is equal to 1 to 3 of minus 1 to the power of k. You can check that when we calculate this, we get minus 2. Likewise, you can check that the second sum is equal to 7 divided by 6, and the third sum is equal to 139 divided by 12. Final example for today's class. I want to find a formula for 1 plus 2 plus 3 plus 4 plus 5 plus 6, etc., all of the way up to n. I want to find a formula for the sum of the first n natural numbers. And the way I can do this is like this. Instead of calculating this sum, I want to calculate 2 times this sum. And then later we're going to divide by 2 to find the formula that we want. We have 1 plus 2 plus 3 plus 4 plus 5, etc. And then we have another 1 plus 2 plus 3 plus 4 plus 5, etc., which I'm choosing to write in the opposite order. So instead of starting at 1 and then plus 2 plus 3, I'm starting at the biggest number, n, and then plus n minus 1 plus n minus 2, etc. And I'm doing this because if we look at the numbers on top of each other, we have 1 plus n. And then we have 2 plus n minus 1. And then 3 plus n minus 2. And so on. All of these numbers, these pairs of numbers on top of each other, are equal to n plus 1. So we have n plus 1 plus n plus 1 plus n plus 1 plus n plus 1 plus n plus 1, etc. How many n plus 1s are we adding together? We have n of them. So this is the same as n multiplied by n plus 1. And then finally, we can divide by this number 2 to find the formula that we want. The sum from k is equal to 1 to n of k must be n multiplied by n plus 1 divided by 2. We're going to use this formula later in the course. 2 more formulae that we're going to use later in the course, which we could prove in a similar way, but they're more difficult, so I'm not going to do them. The sum of the first square numbers is n plus 1, 2n plus 1 divided by 6. And the sum of the first n cubic numbers is n plus 1 over 2, all squared. And that is the end of today's lesson. Next week, we're going to start talking about geometry. We'll study polar coordinates, conic sections, and then three-dimensional Cartesian coordinates. Before I ask for questions, let me tell you that the first homework is available. If you look in OLearn, find the homework link on the left, and then scroll down. You will find homework 1. The questions are in a PDF file, which is linked here. You'll see there's the blue writing 2020 to 21 architecture homework 1.pdf. Click on this file, you'll find the questions. You can print this out, solve the questions on paper, and then after you're ready, click on the title homework 1 and enter your answers using a multiple choice test. Are there any questions? Okay, the way that my lessons work is once I get to this orange screen and I say I'm finished, we have an hour for you to ask questions if you want. If you don't have questions, you're welcome to leave any time that you want.